So we're ready to begin our last block of lightning talks. I could do 3 more of these. These are so interesting and engaging, and I'm just so excited to hear what's been going on in all corners of our research network. So our first speaker in our third and last block of lightning talks is Erica Fischer, an associate professor at Oregon State University. So welcome, Erica.
All right, so we're going to switch gears for a second. We're going to talk about wildfires, but in this talk, I'm going to try and continue the conversation that David started at the end of the last session, focusing on housing. So the infrastructure and design within our communities is not considering the intrusion of wildfires. This is mainly because wildfire mitigation and adaptation has mainly been researched by land management agencies, excluding many of us in this room. Therefore, mitigation and adaptation practices and designs are meant for the wildland and not for the communities. And we're left with prescriptive mitigation approaches for our infrastructure and single-family homes. The fire exclusion policies enacted throughout the 20th century, coupled with climate change, make it impossible for this hazard to only be mitigated within the wildland. We must be mitigating within our communities. Wildfire response as well as urban response are becoming overloaded, leaving us with devastated communities. When fire is propagating through the wildland, our vegetation is the fuel. However, when fire is propagating through our communities, it is our single-family homes that are the fuel for the fire, which is why we have to think about the design and mitigation of these single-family homes. And so what do we do for communities that look like this? Well, first off, we have to acknowledge that fire is a natural occurrence within our landscape. Our flora and our fauna actually benefit from fire within our landscape. And so we cannot continue the fire exclusion policies that were enacted during the 20th century. Also, as a Nahiri community, we know that our critical infrastructure components need to be protected. And so what is the connection between the fire and these critical infrastructure components? And this is where our homes come in. So our homes are the assets within our communities that need to be protected, as David pointed out in a previous talk, but also it is the fuel within our communities that need to be protected against so that we are not overloading our fire response. And so if you think about what the mitigation practices are today, a lot of it is centered around defensible space. And what does that actually mean? Well, defensible space means that we are clearing our land of ignitable material around our house so that our house can be defended. Just as in other hazards, our mitigation practices are focused around life safety, not asset protection. So for our fire response to be able to defend our homes, we need to reduce the intensity of our fire within our community, and that is going to occur by reducing the amount of ignitable material around our homes. In addition, the most common fire spread mechanism within communities are embers. Embers can fly up to 2.4 kilometers and even further in these wind-driven events that we're seeing, such as the one in Lehigh, such as in Paradise, California, such as in Oregon in 2020, Colorado in 2021, and in Santa Rosa in 2017. This means that every home within 2.4 kilometers of an individual home can threaten that home for igniting. We understand the concepts of community resilience in this room. We have done tons of research that community resilience cannot be achieved on a house-by-house basis, property-by-property basis. We need to look at community-wide, and this hazard is no different. And so every community is different. We have various wildland urban interface communities throughout the United States. They all have different climate, they all have different landscape vegetation, they all have different topography, in addition to the designs of their infrastructure and mitigation measures. And so what this means is that we have to be able to move away from prescriptive mitigation approaches, such as in the International WUI Code, into a design of these mitigation and adaptation approaches approaches that we can use based on science and research. And so this is where all of you come in. Right? We have to be able to understand how do we decouple all of these individual mitigation measures and adapt them for the communities as it makes sense for them. And so we can mitigate on different levels. We can mitigate on the parcel level, and this is removing the ignitable material around the house, reducing the intensity of the fire as it encroaches the house. We can actually mitigate on the home itself. Home hardening will reduce the likelihood of ember intrusion within the house so that the home is not igniting from the inside out. But there are also community-level mitigation measures. How close are our homes to open spaces that are burning? Or what are the pathways for fire intrusion into our communities from those open spaces? What is our home-to-home spacing? In some communities, our homes are spaced so closely together that they are in each other's defensible spaces. What do we do? How do we mitigate within those types of communities? What is the egress and access to our communities for firefighting? And what is a proximity to fire hydrants so that our homes can actually be defendable? So this here community is really primed to start research on this topic, and I hope that you all will attend the session tomorrow where we're going to talk about how to enter into this field of wildfire research, how there are many researchers within this room performing research in this space, and they didn't all start here. How can we use our knowledge from other hazards and apply it to this hazard? How can we talk about building transdisciplinary teams, as many researchers have talked about today, to really solve this problem? And what do we need experimentally, numerically, and from field data collection to be able to systematically collect data on our homes and what is causing home destruction in these communities? I also want to thank Nora for all of her work in the decadal visioning study and featuring wildfires prominently for future research in this space. And thank you all so much.
Great. Thank you, Erica. Our next speaker is Jim Ricles. He's a professor of structural engineering and the director of the NERI experimental facility at Lehigh University. Jim.
Yeah, thanks, Jennifer. Well, good afternoon, everyone. I'm going to present to you a talk. It's just an overview about some advances in cyber physical simulation, and this represents really some synergy between two NERI sites, in particular FIU and Lehigh, and we both joined forces to create, I think, something very special. So I'm not going to mention all the names, but you can read them, and I think Amal and Narimdam are actually here, so we volunteered, and they're going to answer all the questions, and I get to give you all the overview here. In any event, let me first make a problem statement here. And as we know, we've been talking about resiliency, and it's rather challenging. I'm just focused on tall buildings when we look at the complexities of the wind motion and the way that the structure deforms, and more so if you have to evaluate response modification devices to make the system more resilient. That could be very challenging if we don't have the right motion in the system or the right loading. And so this makes it rather difficult and challenging now, and not to badger traditional wind tunnel testing, because things have evolved, but what's often used there is rigid aerodynamic models, and so they're easy to construct, but they ignore elasticity, aeroelasticity, and in some cases, is that important or not? That's something we actually try to understand better. More so, if you don't have the right motion in the structure, how are you going to evaluate how well a response modification device does if you don't have the right motion to begin with? And so that's a challenge. So if you take a step back and look at what we've done in earthquake engineering, is we've tried to use a synergistic approach in which we define the whole system, and where you define the system, it's up to you. It could be the whole city block, but you define the whole system. In this case, I define it as a civil infrastructure and the environment. And we're going to discretize this into two domains. I'm going to call it cyber. Sometimes it's called hybrid, but cyber, and then there's the physical. and then demand is imposed on both, and both of these are synchronized together. And the cyber is the analytical substructure. That's something you can model really well. And if you can model everything well, you don't need anything else, but you usually can't, particularly on response modification devices. And so that's the physical domain, for which there's no really good numerical models. You have to model that physically, but you got to link all this together. And so we used, and think about the approach, you developed this technique, real-time aeroelastic hybrid simulation, in which we have an experimental substructure. I show some dampers here in this tall building. They're in the tune mass damper in one direction and the outriggers in the other. And we have this aeroelastic, sorry, things got ahead here. I don't know what happened. I just lost all my time. So anyways, we have an experimental substructure, aeroelastic substructure that's defined, and it's coordinated and synchronized with a new substructure, which is an aeroelastic substructure. And this aeroelastic substructure is there, but nothing else to measure the wind pressures when the system's put into the deformed mode. So it will give you the right wind pressures, and your response modification devices could be in a separate substructure, so you don't have to interfere with the instrumentation or the motion of that structure. And so we applied this to this tall building, in which there's the experimental substructure, the dampers, and this outrigger system. I already explained the tune mass damper. There's the analytical substructure is the remaining part of the system, except for the aeroelastic component. That's actually in the wind tunnel at FIU. And so we applied this, and what did we find? Well, I'm only presenting you some of the results. We found a significant reduction in the roof accelerations. I mean, appreciable. And this was achieved by applying these response modification devices, which we had to model physically, because the numerical models really were not very accurate. Now, the other thing that's important is coming back to the aeroelasticity effect. We went back and looked at the rigid aerodynamic test, and then we looked at the aeroelastic effect that we had. And what did we find? Well, you look at the pressure coefficients, and where was the pressure coefficients used? In the codes for designing your structure. We found it up to 40% difference, right? They could be plus or minus, so that could have a significant effect, I think, on the design. And so with that, I just want to express, or thanks, with collaboration with FIU. I think we offer now to the stakeholders and other researchers that technique to try to better understand in wind tunnel testing how things really would perform out in the real world. But more importantly, we've developed a synergistic approach to training the next generation in cyber physical simulation. And with that, I want to thank you all, and also acknowledge NSF, who sponsored both our facilities. Thank you.
Great, thank you, Jim. Our next speaker is Zsarnóczay from the Sim Center at Stanford University, where he's a research engineer and deputy director.
We don't have much time. We all see that the number of natural hazard events with serious consequences increases year by year. We cannot afford to spend a decade or two in waiting for our new ideas to spread through the traditional feedback loops. This is where NERI comes into the picture, where we all understand that building active connections between each other will foster collaboration and lead to enhanced and increased number of creative discoveries. At the Sim Center, we believe that a part of this is open and shared resources that will make a big difference. Think about OpenStreetMaps, or if you are a structural engineer, think about how much OpenSeas has helped us in the last 2 decades. At the Sim Center, we are building an open simulation platform to serve a broad range of simulation needs in the natural hazards engineering community. On top of this platform, we are building domain-specific applications to help support and train the next generation of experts in our field. Education is an important part of our mission, and today I brought an example to emphasize the critical need for education to fulfill the collaborative vision of NERI. My example is from the field of earthquake engineering, because we have already made strong collaborations there, and we have already contributed to the advancement of that field. It all starts with software. Our software needs to be capable, easy to use, transparent, reliable, robust, and the list goes on. But besides looking at these requirements, our team also emphasizes early engagement in education. The performance-based engineering application that I have in this example has been used at universities to teach graduate students in seismic performance assessment in over 5 years. Besides these courses, we also developed tool trainings and online webinars so that we can access even more students. And over these 5 years, we have brought this tool to more than 1,000 students who have developed active working experience with it. Many of these students found their way to jobs in leading firms in industry, where they have created new opportunities for those firms through working with these tools and through the collaborations that working with open platforms can bring. Some of these firms went even further, like Arab, who decided to open source their own recovery simulation methodology and share it with the community through our platform. We always help these firms get started with our tools so that they can find it easier to transition from their existing workflows to the ones that these open tools provide. Now, when it comes to those students who stay and do research, they benefit from an active connection between industry and academia so that they can identify questions that do not only have intellectual merit, but also promise broader impact. Several research ideas have benefited from the interactions, the common vocabulary, and the shared computational simulation tools that we provide. We have also contributed to moving the earthquake engineering field and the high-fidelity simulations in that field from single buildings to looking at portfolios and looking at regional scale impact. Through working with these practitioners, students, and researchers, we gain experience about what their needs are, and we can adapt and prioritize the features in our tools so that they can keep serving our community. Now that we have a working ecosystem, it is obvious that there are benefits for everyone in it, and the number of users and the number of people working in this space is increasing rapidly. My takeaway from this example is how important the early education was to achieve these results in such a relatively short time. And the question is, how do we replicate this success in a broader scale so that we can really support disaster recovery and community resilience? We are working on a number of different applications, and each addresses a different area of natural hazards engineering. And we are actively building similar ecosystems in all of those areas so that they can all come together and contribute to reaching our end goal of community resilience. We are also working with a large number of individuals who are already believing and supporting our vision of an open platform. You see, just from today's lightning presenters, there are all of these people who are already collaborating with us and are at different stages of working together with us on different topics, as you can see. So this is not limited to earthquake engineering, and there's even more topics if you go beyond this group. But just imagine how much we could accomplish if all of us worked together. So whether you're a student, a faculty member, or a practitioner, I encourage you to join us, because it is collaboration that holds the key to really solving our grand challenges. And there are many of us from the Sim Center here in the room today, and we are eager to talk to you and discuss how you can get involved and how we all can work together. So please visit us at the poster session. We have a session tomorrow with Greg Dearline, and we have workshops on Thursday that all provide you an opportunity to learn more and to see if you can benefit from this system. Thank you very much.
Great, thank you, Adam. Our next speaker is Claudia Marin, a professor at Howard University. Claudia.
Good afternoon, and thank you for the opportunity. My research is on protective systems and AI-driven methods for structural conditions, to extract structural conditions. And today, I'm going to give a high-level presentation on how we can use computer vision to make assessments on structures that no one is paying attention now. Then you see pedestrian bridges falling apart, traffic lights, light poles falling under storms, and we don't have a way to measure or to get data to prevent this happen. If you had data before this happened, maybe you can take action. Then what computer vision does, and the intention here is to extract information, exactly displacement from point of interest, without contact. Usually we have sensors. Then in this case, you don't have contact. Then you are able to get as much information as possible from that. The big picture is that you are using AI, in this part, computer vision, to get displacements and process those displacements. And with just the simple processing, you are able to extract essential information for you to say if something happens. If you like more information, you can go further with machine learning models. Then here we had an example with a full-scale building that was fully instrumented. And by tracking 2 pixels, the red points on the video, you are able to reproduce the sensors data accurately. Then this shows that we are able to use this tool, and it's accurate. We also here have an example about a simulation, the bridge column under earthquake testing. And we are able to see it was fully instrumented. It's very difficult, take a lot of time to get this done. And we are using tracking the pixels. We are able to measure the global responses. The blue lines are the sensor data, and the black lines are the measured by the video analysis. And you see good responses and local responses to just little measurements. And we were also able to detect errors on the sensors. Then this is allowing us to create enhanced data sets, but also to verify the sensors data. Then moving on with magnification and small motion analysis, you will see in the left side video, you are not able to see a movement with the naked eye. If I do magnification, you will see you extract the modes, the vibration modes of the light pole that no one pays attention to this. Then imagine that you are able to extract dynamic properties just by looking at video, and over time, you can see the difference of those properties, and you can stay if there is a compromise on the structure. And a big picture about how we can use for hazard conditions and extreme conditions. You see, this is an example of this roof under strong winds. And imagine an app that you have in your phone to inform you that your roof is falling apart, then you take action before this happens. Then this is not only helping me to go to the side, I'm sorry. I didn't plan to get this. But this is just the fun we had with the students. And it's very easy for me to engage with them, to go to get real data on the field. And now they are presenting. They value contribution from different disciplines. I'm working with computer science students and civil engineering students, and they value how they contribute to the problem. Then this is something fun for me. This is like my hobby. And in conclusion, this is a powerful tool for us to think about it and continue evolving. And it's not only helping us to get good data, but also engaging students in this field. Thank you.
Thank you, Claudia. Our next speaker is Alia Amer from Lehigh University, where she's a postdoctoral researcher. Alia.
Hi everyone, my name is Alia and I'm a postdoc at the Lehigh experimental facility. I'm going to talk more about my journey at this facility as a PhD student and also as a postdoc. So I'm going to start with a very simple question that can summarize all of my research is, do you want to live in a damaged building after an earthquake? Unfortunately, we cannot turn this into a discussion because it's only 5 minutes, but I hope you all agree that we don't want that. So that's why we start seeing the seismic resilience becoming more trending over the years, because we want to develop adaptive systems that can recover quickly after a disaster. In parallel to that, we're shifting to more eco-friendly materials like mass timber to reduce the carbon footprint in construction and build more resilient structures using mass timber. In 2016, the Ricles wood project started, which focuses on using cross-laminated timber self-centering or rocking walls as a low-damage lateral force-resisting system. And you can see, like, after 2016, the trend is increasing because the team is working hard to finish the project. So in order to answer the first question, we need to learn more about the damaged states of the CLT rocking walls. We need to know how they interact with the building as a whole, like floor diaphragm, gravity load system, and we always forget about connections, but connections needs to have the capability to accommodate the kinematics of a building without damage. But when we're talking about kinematics, we cannot really say that we can start testing structures under unidirectional loading because earthquake comes in any direction, and multidirectional loading can be more damaging to structures, and spoiler alert, it is more damaging. So we have to start looking for testing under multidirectional loading. So at Lehigh, we built part of a prototype timber structure. We wanted to design and test a resilience timber structure that has all the components and connection details that we can find in a typical structure. And you can see, like, this is a very quick video about the test sub-assembly under multidirectional stick-link loading. I hope you can see that all the connections can deform or can accommodate the multidirectional loading. And at the right top of the video, you can start seeing localized damage at the CLT rocking wall. So we observe damage in the walls. We quantify this damage with engineering demand parameters, and we can establish fragility functions for engineers to use to achieve resilience in timber structures. And you can see now that the probability of damage in a CLT wall panel under multidirectional load can be doubled if I'm only considering unidirectional load. So I told you now we have a problem, that we have a damage. So at Lehigh, we didn't just leave you like this without the solution. So we designed and tested a proposed repair action for damaged CLT rocking walls in order to restore the initial state of the wall. Now I'll be now the self-centered one, and I'm going to talk about myself and how working in a very big project funded by NSF that includes huge team from academia and industry helped me in my professional development and my career. Familiar faces, I know everyone knows them. So all the acknowledgement comes to my mentors, and I came to Lehigh with, I can proudly say it, with zero experience working in a lab, especially in large-scale testing, but having the right environment and the right mentors that genuinely invest in young engineers completely changed the game, and most importantly, they come and work with us in the lab, so it's super fun. Like 2 weeks ago, Professor Ricles and we were whitewashing a specimen together, so it helps a lot for you as a young engineer and as a female specifically that has no experience. There's a lot of things happening behind the curtains when you do large-scale testing that I have to learn a lot about sensors, I have to design control algorithms, checking stability of actuators. All of these things cannot be really mentioned in a dissertation, but it definitely helped me a lot becoming a successful researcher. Again, I said I came to Lehigh with zero experience working in the lab. The next thing I know is that I was responsible to run a 2 million pound collector test funded by NSF. And this is me and Tommy Marullo, research scientist at Lehigh. And this is our size next to the specimen. So I'm super lucky to work on the 2 biggest projects in Atlas. Thank you all, and please come to our poster session to ask more about the facility and also my research.
Thank you, Alia. So our final lightning speaker for the day is Professor Joe Wartman from the University of Washington and the director of the RAPID facility. Joe.
Thank you, Jennifer. So I think it's fair to say that today we cannot reliably forecast the health impacts of major natural hazard events. But there's growing interest in this topic, and we're making progress, and sometimes the results are surprising. My own work focuses on the impacts of landslides on communities and individuals. This is one such community. This is La Conchita in California. Over the past several decades, multiple landslides have affected this community and have claimed the lives of 10 individuals. And we typically look at this problem through a risk perspective, and this is the equation many of you are going to be familiar with. Risk is the likelihood of a hazard, and then given that that hazard occurs, what are the consequences of that event? And of course, that's a distilled version of a much longer probability equation that relies on the relationship between the magnitude of the hazard event and what the outcome is. And so we've traditionally used some general rules of thumb, some approximations in order to find the relationship between landslide inundation depth, which is the depth of the landslide when it strikes a structure, and the likelihood of survival. And so my graduate student, William Pollack, and I did some work in trying to develop an empirical database to really refine that relationship. And so we relied on a number of open source records from the public health data, from government reports, from reconnaissance reports. We ultimately came up with 334 case histories that populate this database. But I want to say that really at its heart, this is field reconnaissance data on the horizontal axis, such as that we collect at the RAPID facility and help others collect. And on the vertical axis is public health data. So this is what it looks like. And you can see at the far extremes, there's some not surprising relationships. When you have very big inundation depths, the likelihood of survival is quite low. And alternatively, if you have very low inundation depths, you're likely to survive that event. But when you apply statistics to this data, you find that overall there's a very poor regression coefficient. This is not a very good explanatory variable. And most importantly, there's no statistically significant correlation between inundation depth and loss of life for that portion where we have most of the data, and for most of the kind of real world examples. And so that means that something else explains survivability. It's not the size of the event as we have traditionally thought. So we went back and looked at eyewitness accounts. We went back to a lot of press accounts, a lot of survivor accounts about what actions were taken, about accounts of those who were lost, and about accounts of those who were survived. And we did a statistical analysis to look at what kind of factors were correlated with loss of life. And what we found is that human behavior really explains and really drives survivability in these large landslide events. And it's for several reasons. First off, we know that simply being aware that you're in a landslide hazard area promotes action when there are precursory signals, which are usually audible. And secondly, we know that individuals who move upstairs or who are permanently situated upstairs, particularly in the evenings when they're sleeping, have a much higher likelihood of survival. In fact, it's an order of magnitude increase in odds of survival. And so that means that some small modifications, such as moving upstairs during periods of extended risk, can increase your likelihood of survival. So those kind of small human actions can really reduce the overall risk. You can also learn a lot if you look at the lower left side of that diagram, and this is the case of individuals who survived under very adverse circumstances. We took a lot of those accounts and we distilled those into some lessons learned and some protective actions that can be taken. They've been reported in the press. They've been simplified into community guidance documents that have been distributed to communities who are at risk of landslides, and we have full details in a paper that accompanies this study. I want to close by saying I was really excited to read the visioning report for a whole slew of reasons, of course, I think as many of you were, but I do want to quote a couple sentences from the report. The first is that highlights the need to account for human behavior when predicting outcomes of natural hazard events. The second is to effectively assess hazard impacts on public health, but also on well-being and on mental health. And then third is to promote collaborations across federal agencies and government agencies, including specifically NIH, among others who are mentioned here. And I want to say that we're doing that today with the RAPID facility with supplemental support of the National Institutes of Health. We're now acquiring new instrumentation to assess environmental health and public health, and so we'll be able to make those measurements directly in the field at the same time we're collecting LiDAR data and drone data, and enable us to more directly connect the impact on health. And so I think that we have a vision. I think we have what's coming very soon are the tools in order to do this. And I think that we as a NERI community now have the opportunity to really make significant progress in understanding the human dimensions of disasters and also to reduce the impact on our human health and on community and enhance community resilience. So thank you.
Thank you, Joe, and thank you to all of our speakers. Let's give a round of applause for all of our lightning speakers, our panelists, our keynote speakers,